So let's talk about the limit definition of the derivative in three different ways. We're going to look at quadratic functions, we're going to look at square roots, and then we're going to look at fractions or rational functions. So let's dive right into our first function. Here we have a quadratic. So notice how I've already written the limit definition of the derivative, and what we're going to do is we're going to apply this in those three different type of function contexts. All right, so here we have our first function. F of x is 3x squared. We have a quadratic. Now what we're going to do is we're going to apply the limit definition. Make sure that you write limit as h goes to 0. You are, in fact, taking the limit. And now what we're going to do, and so do that every single step. Now what we're going to do is, in place of x, everywhere there's an x, we're going to plug in an x plus h. So that's first. So rather than 3x squared, inside the parentheses, we'll substitute in an x plus h squared. And then we'll subtract just f of x. F of x is good old 3x squared. And this is all over h. So this is always going to be the first step, no matter what you're taking the limit definition of the derivative of. You plug in x plus h, and you subtract off just x. So you have that difference, and you're taking the limit as h goes to 0. Okay, so now let's keep simplifying this. Again, make sure that you write the limit as h goes to 0. Whatever calculus class you're in, if this is being graded, you want to make sure that you don't forget to take the limit and that you're really showing your work and being accurate. Okay. So now let me just do a little scratch work over here. X plus h squared. Now be careful. Sometimes students want to distribute the square. Say that this x plus h quantity squared is equal to x squared plus h squared. But be careful. When you square something, you're really multiplying it by itself. And if you're multiplying it by itself, you're really just going to use the distributive property. You might call this FOIL. X times x is x squared. It's just the distributive property. You have hx, you have another hx, and last but not least, you have h by h. H times h is h squared. So this simplifies to x squared. Combined like terms, you have two hx's, and you have h squared. So I always like to do this sort of scrap or scratch work on the side, just so you can show your work really, really cleanly. So we have 3 times the quantity x plus h squared. Our scratch work says that that's equal to x squared plus 2hx plus h squared. And we're subtracting off 3x squared, and this is all over h. So we're just going to keep going with this. Now, do not forget to distribute the 3, meaning multiply each piece or part by 3. And now we get to the sort of canonical spot. This really pretty much always happens, and it will always happen in the examples I show you. Certain things will cancel. So look for that cancellation of non-h terms. What do I mean by that? We have 3x squared and negative 3x squared. Those are opposites. There's no h involved in either of those terms. They should be opposites. Don't force them to be opposites, but they should be opposites and they should cancel out. And so that will happen really every single time we do this. And so after we've canceled out the non-h terms or the x terms, what we'll do now is we're going to factor. So let's give this a whirl, shall we? What we can do is we can pull out an h from the numerator, and that's really like a checkpoint. If we factor out h from 6hx, h times 6x is 6hx, and 3 times h is 3x, h squared, excuse me. And so we're just going to keep going with this. But so this is I'm going to draw some lines here. This is like a really common theme. You're going to factor out h. All right? Now, the whole reason why we factor out h is we can now cancel. H divided by h is 1. And finally, we can just take this limit. We have 6x plus 3h. This is all over 1. We can plug in 0 for h. So we can actually let h go to 0. 3 times 0 is 0. And we just get 6x. So f prime of x equals 6x when f of x equals 3x squared. And we were able to show this quadratic's derivative using the limit definition of the derivative. All right, now let's take a peek at a square root function. So we're going to do the same sort of process. Let me just highlight that process again. The process, what we'll do is we'll substitute. You know, we plugged in the x plus h for x using the limit definition of the derivative. Then we did some algebraic simplification. All of the terms that didn't have h in it canceled out. We were able to factor out an h to kind of get rid of this h in the denominator, cancel it out with an h in the numerator. And then we can plug in. We can substitute in 0 for h because we're no longer dividing by it. And then we have our final answer. So now let's try a new function. Let's say we had g of x. So here will be our square root function. Let's say g of x is 2 root x, and we're just going to apply the limit definition of the derivative. We have the limit as h goes to 0 of f of x plus h. So recall, wherever there's an x, now we're going to throw in an x plus h. And then we're just going to subtract off the original function, which really this is g of x, but you could say f of x, g of x, a of x, b of x, whatever the case may be. And this is all over h. So again, that first step, you just want to plug in x plus a little bit, x plus h in place of x, subtract off the original function, divide by h, and make sure that you're taking a limit. All right, let's keep going with this. All right. So whenever you have a square root function, you are going to multiply by the conjugate. So let me take a little sidebar over here, and let me remind you of what happens when we multiply by a conjugate. So you've probably seen the conjugate in a variety of contexts. Perhaps if you had something like x plus 3, its conjugate would be x minus 3. And when you multiply them together, something interesting happens. The first two terms multiply together, but the inner and outer, or those middle terms, if you will, when you distribute, they cancel out. You have plus 3x and minus 3x. Those are additive inverses. They make 0. And then you have what's on the end. Now, another way that I could write this is like so. It turns out that the first term is squared. The inner and outer terms cancel. This is by design. This always happens when you successfully multiply by conjugates. And then the last term, you'll have the last term essentially squared. So we had the first term squared and the last term squared. And notice we had a positive times a negative, so that made a negative. So you might say, well, okay, can I see a conjugate with a square root? Let's say I had the square root of x minus 1. Its conjugate would be the square root of x plus 1. And then the first two terms would multiply together. That's root x times root x, which is good old root x squared, if you will. The inner and the outer terms will cancel. You'll have minus root x, and you'll have plus root x. Those are going to cancel. Then you'll have minus 1. So those will cancel, and we'll just have a good old-fashioned x here. Now, really, it's the absolute value of x, but let's not get too crazy here. So now we have x minus 1. So it's kind of interesting when you multiply a radical by its conjugate, you can get rid of that radical or that square root. nice. So we're going to do that same sort of thing here with this example. All right, so goodbye conjugates. Okay, so we're going to multiply this by its conjugate. Now, you can't just multiply the numerator by its conjugate. By the way, this is obviously a little bit more complicated than the motivating examples. When you're crafting a conjugate, you want to have it look exactly like the original problem. The only thing that's different is that sign in the middle should be the opposite. So it's sort of like an evil twin or a doppelganger. And you can't just multiply the numerator by that. You also have to multiply the denominator by the same thing. So why are we allowed to do this? Well, we're just multiplying by the entire expression by 1. All right? And so you're allowed to multiply something by 1, and you'll change the way it looks, but you won't change its value. We call that the multiplicative identity. So if we multiply the top by its conjugate, we'll multiply the bottom by the same conjugate, because we're really just multiplying by 1. Giant number 1 there, because anything divided by itself is 1. All right, now, whenever you work with conjugates, so now we're going to first just rewrite the denominator. We have h times this lovely mess over here. Don't distribute that out. That's always a recommendation I have. Just leave the denominator a mess, and that's fine. The numerator is going to simplify, and then eventually we'll be able to cancel out an h from the numerator with an h in the denominator. So that's why we're going to leave the denominator as is. And then, we'll eventually take the limit in the denominator, and it'll all turn out nice and clean. Right now, let's take advantage of the fact that we're multiplying by the conjugate, and we'll multiply the first two terms. 2 times 2 is 4. And then we have a root x plus h multiplied by root x plus h. That's just x plus h. Now remember, let's sort of motivate that a little bit. Remember we did our motivation with conjugates a little bit earlier, but let me just show you. If I have root x plus h multiplied by itself, that means root x plus h, the quantity is squared, therefore the square and the square root can essentially just cancel out for all intents and purposes. Okay? So they do just cancel out. You have what's underneath, just the x plus h. And then the inner and the outer terms, if you will, when you distribute this, they're going to cancel out. Then the final term, you'll have a negative times a positive. That'll result in a negative. 2 times 2, which is 4, and the same vibe with the root x multiplied by itself. You have root x multiplied by itself. That's the same as root x squared, and then the square and the square root will cancel out. Their inverses or opposites. So this just turns out to be 4x. Now we're just going to clean up the numerator and simplify it away. So we'll distribute. That's a common step with the simplification. Everything else is, the same. We are not going to forget that we're taking a limit because we're using the limit definition of the derivative. The denominator is unchanged. And now we can cancel out all non-h terms. That always happens if you're doing things correctly and being careful with your signs. So that's a good step. Now we can even go a little further here. So we're still taking the limit. We're just shaping this. We have a 4h in the numerator, and we have an h down low. Since we have multiplication in the numerator and the denominator, we can just say, well, h divided by h is 1. So we can kind of pull out that h over h, which is just 1. That 1 will be multiplied by the leftovers, and we can just write this more simply. And we're just slowly shaping this and cleaning this up. What's nice is we left that denominator as is. Now we got the h to cancel. Now we can just take the limit, just send h to 0. this will just become, limit as h goes to 0, 4 over, well, x plus 0, that's just x underneath that first radical there. And then you have another 2 root x. Now we'll just keep simplifying this. Don't forget to write limit each time. Now in the denominator, you have 2 root x and 2 root x. Let's combine like terms. So that means you actually have 4 root x's. But look at that, 4 divided by 4 is 1. So a 1 still remains in the numerator. Oh, and by the way, just to be clear, we already took the limit. So, you know, get rid of that mathematical notation right here, right? We sent this to 0, so now we're just cleaning up. We don't need to say the word limit anymore because we took the limit. And our final answer is 1 over root x. So 1 over root x, that is the derivative of our function. Our function here is g of x. So we'll say this is g prime of x when g of x equals 2 root x. So we were able to find the derivative by multiplying the conjugate and simplifying. And just to kind of run this back real quick, we multiplied by the conjugate of the region that had the radicals in it. We kept the denominator as is. We multiplied it out. It cleaned up quite nicely. We distributed. We canceled out h. Combined like terms, simplified after taking the limit, and everything was gravy from there. So this problem, this category of limit definition of the derivatives, these radical or square root problems, they really take some time, energy. And last but not least, let's use the limit definition of the derivative on this function right here. A fraction, or a rational function, if you will. So we'll do what we always do. We'll be taking the limit as h goes to 0 of 1 over x plus h minus 2. So that's k of x plus h, if you will, minus just good old k of x. And now I can either write this all over h, or if you want, even from the get-go, you can just say it's multiplication by 1 over h out front. Dividing by h is the same thing as multiplying by 1 over h. It's kind of like dividing by 2, like if you were dividing something by 2, you're splitting it into 2 equal parts. You were taking half of it. So that's multiplying by a half. Taking half, multiply by half is the same thing as divide by 2. So dividing by h is the same thing as multiplying by 1 over h. Okay, so let's keep working with this. We have this situation right here. Now, what we're going to want to do, you kind of always want to fall back on the things that you've learned or the things that you've done in the past. Like lots of times in calculus, if there's a quadratic, you might want to factor it. You now know if there's a limit that you're taking that has a square root in it, you're going to multiply by the conjugate. If there's some fractions, you might want to get a common denominator. You have to have that inspiration. So we'll get a common denominator here. We're going to multiply each of these fractions by the other. And so you can't just multiply the denominator by sort of the other denominator. So you have denominators of x plus h minus 2 and x minus 2. You have to multiply the numerator and the denominator by the same thing. So we're really just multiplying by 1, okay? That's the only way that you can change the way something looks. I might even throw this 1 over h out front just to kind of get it out of our way. Now we can multiply numerators. We'll keep the denominators factored, if you will. And then over here we have negative 1 times the quantity x plus h minus 2. Be very careful, make sure you include those parentheses. So we're just going to keep on churning through this limit. We've gotten a common denominator so that we can subtract the numerators in this case. So we have x minus 2, and we'll distribute the minus x minus h plus 2, and we'll leave that denominator without distributing, and we'll just leave it as is. Now, notice all the non-h terms cancel out. X and negative x, those are additive inverses. They make nothing. Negative 2 and positive 2. Goodbye. Ooh, so this is actually really nice. So we have the limit as h goes to 0. I keep sort of playing with where this 1 over h is, and that's okay. It's all just multiplied together. Now we have h in the numerator and h in the denominator. H divided by h is 1. So there's still a negative 1 up top. So we have negative 1 over the limit as h goes to 0 of x minus 2 times x plus h minus 2. So that checkpoint of getting all the non-h terms to cancel and then being able to factor out and cancel out an h from the numerator and denominator, that really happens like every time, no matter what sort of limit definition of the derivative you're calculating. And then from there, since we kind of got rid of that pesky division by h, we can finally take the limit. We can just send h to 0. And so now you have x minus 2, and then you have x plus 0 minus 2, which is another x minus 2, really. You add 0, that's not going to do anything. So you have two x minus 2's multiplied together, which means they are squared. So our original function was k of x, and we just found the derivative, k prime of x, to be negative 1 over x minus 2 quantity squared.